Hi, this is Professor Fernandez, and we are asked in this example to solve this fourth order homogeneous linear constant coefficient ODE, and we're in class notes C in lesson 7. So what are we going to do? So we are going to use what we've learned in this lesson and write out the characteristic equation of this ODE first. So that is r to the fourth minus 3r cubed plus 3r squared minus r equals 0. And then we're just going to try to factor this as best as we can. So first thing we can do is we can factor out an r. So this gives us r cubed minus 3r squared plus 3r minus 1 equals 0. You may recognize this as something that can be factored very easily, but that would mean you memorized some, at the time in high school somewhere, some obscure fact. So what I'm going to do is use this as an opportunity to review how you would factor this parenthetical term without remembering that obscure fact. And certainly r equals 0 is one solution, and then we're going to try to find set this equal to 0, find other solutions. How would we do that? We would say, well, I can't remember. This is kind of complicated. Let me just illustrate first. We can try factoring by grouping r minus 3, but then there's really no way to get rid of that 3 from the r. If I factor out the 3, I will get r minus 1/3, and this doesn't seem to be working out for factoring by grouping. So another method, in addition to factoring by grouping, that you can always try, is if you can spot a root, you can do some version of long division or synthetic division. So what is the root that we can spot here? Sometimes you can do that by trial and error. All right, so if I try the simplest possible quantity. So if I try r equals 0, that would be 0, 0, 0, minus 1. That doesn't give me the 0 that I want. Okay, so r equals 0 does not solve it. Let's try r equals 1. So that would be 1 minus 3 plus 3 minus 1. So these cancel, and then these cancel. So actually that does give me 0. So r equals 1 is a root, all right, of this third degree polynomial. R equals 1 is a root. Okay, that means that r minus 1 is a factor. All right, so what I'm going to do now is remind you of how long division works of polynomials. And this is a technique you may have learned some time ago. It is also a technique that looks very intimidating, but I'm going to remind you of how this works, by copying the steps in dividing, I don't know, let's say 25 by 7. All right, so, and again, you may or may not have learned how to do it this way. So there are also all sorts of possibilities. But we are talking here about long division of polynomials. Okay, and this can also be done using synthetic division. Okay, so if what I'm about to do makes absolutely no sense, you've never seen this, this elongated L version of division, and you've never heard these terms before, I would still encourage you to sort of listen in, but I've put these terms here on the left so you can look around for extra resources for that. Okay, so in long division, we're going to ask ourselves the first question that we normally ask ourselves in division over here. We say, how many times does 7 go into 25? Right, by which we mean find the number which, when we multiply it by 7, gets as close to 25 as possible. And certainly the answer is 3, without going over. Certainly the answer is 3. Okay, so 3. So then we put that number up here. Because 7 times 3 is 21. And 7 times 4 would be 28, goes over 25. So I will ask myself the same question here. How many times does r go into r cubed, right? What can I multiply r by to get r cubed? And the answer is r squared. So I'm going to put that over here, just so that I'm lining up the columns of the r squareds. Okay, and then going back over here, what's the next step? We say, oh, okay, 3 times 7 equals 21. Okay, so again, I'm going to mimic the step here. So I'm going to multiply r squared times this entire thing. Okay, so what do I get? I get r squared times r, that's r cubed. And then r squared times -1, that's minus r squared. Great. And then going back over here on the right-hand side, I multiplied 3 times 7, I got 21, and now I subtract. Okay, so I'm going to do the same thing here on the left-hand side. I'm going to multiply by a negative sign. Okay, that's how we would subtract these two in this more general fashion. And then on the right-hand side over here, I draw this line, and then I do the subtraction. 25 minus 21, that's 4. Great. So over here, I'm also going to do the subtraction. So I have r cubed minus r cubed, so that gets rid of the r cubes. And I have negative times negative, that's positive r squared. And I'm subtracting 3r squared. So r squared minus 3r squared is negative 2r squared. Okay. If there were any numbers here, right, if I was doing, on the right-hand side, if I was dividing 7 into 259 or something, right, I would keep going. But at this point, we have gotten to the point in the long division where we just repeat the steps. So I'm going to bring down this entire quantity, plus 3r minus 1, and I'm just going to keep going asking the same questions, right? How many times does r go into minus 2r squared? Right? What quantity can I multiply r by to get minus 2r squared? And the answer is minus 2r. And now I'm going to multiply minus 2r times this entire r minus 1. So minus 2r times r gives me minus 2r squared. Minus 2r squared. And then minus 2r times -1 gives me positive 2r. That goes here. All right, and then what I do is I subtract this from the top. Okay, to do that, again, minus 2r squared times -1, that gives me positive, and therefore that cancels out with this term. And then this minus goes over here and gives me minus 2r, and I'm adding 3r, so I have 3r minus 2r, that's just r. And then that's it. There's no other term here to subtract or add with -1. So r minus 1. Okay, and then you notice that I am left with the exact thing that I started off with, so that's nice. The next question is, how many times does r go into r? What do I multiply r by to get r? And the answer is 1. So I put a +1 up there. And then I multiply 1 by r minus 1, and I get r minus 1. And then I would change the sign. R minus r is 0. -1 plus 1 is 0. So I have no remainder, right? There is nothing left. So it turns out, the takeaway, right? It turns out what we have discovered is that the r minus 1 factor that we found factors this cubic polynomial into a very nice quadratic with no remainder. So I'm going to write down here what the takeaway is. So we have found that where we were with the cubic polynomial up here, right, this now factors into an r minus 1 factor, and then this quadratic factor, r squared minus 2r plus 1. Great. So that certainly makes life a little simpler, because now I'm down to a quadratic, and I can always use the quadratic equation to find the roots for that part. But I'm going to keep going, because I'm going to ask myself, I am at a quadratic polynomial, can I factor that? And the answer here is yes. So you might recognize this as a difference of squares. Right, so this is r squared minus r times 2, that gives me that term, plus -1 squared, which is +1. Great, so that tells me that I have a really, really nice and interesting form for this version of the characteristic equation, right? It collapses into something really simple to analyze. I have roots r equals 0, and then 1, 1, and 1, right? I have a root 1 3 times. So that was really, there are two purposes in doing this example. One of them was to remind you about long division or synthetic division, again, whichever one of those you're familiar with. for polynomials. And the second was to illustrate this second case in this lesson. In particular, what happens when you get a repeated root. Because in the second order ODE case, right, the root could only repeat once because there were only two roots for a quadratic characteristic equation. Now, in the nth order ODE case, the roots could repeat a bunch of times. So let me go back up here and remind you what happens if you get a repeated root. So that is this second case over here. So if all the roots are real, but some are repeated, right, then we're looking at the multiplicity of the repeated root. So suppose this is a factor of the characteristic equation, right? We just got something very similar. We got r minus 1 cubed as a factor, right? So in this case, k would be 3, right? Then that number k, the number of times the root repeats, is called a multiplicity. And then what happens? Kind of what we saw in the CC solved case, where t e to the rt was the second fundamental solution, the independent solution to the repeated root case there. Here you just kind of keep going, right? So the first one is the e to the rt, the usual one. The second one is what we got from the CC solved case. The third one, you just keep adding powers of t. So the third one would be t squared, e to the r1t. If the root has multiplicity 3. If it has multiplicity 4, another solution would be t cubed e to the r1t, and so on until the power of t is 1 fewer than the multiplicity of the root. So I'm going to apply all of that in the example that we are working on to finally write out the solution to this example. Okay, so first thing is we go back and then we write out. So this root generates an e to the rt solution, but r0. So that just generates a constant, right? So I'll just put 1 there. And then these 3 repeated roots, this is k equals 3. This is the multiplicity of 3. So this is going to generate for us 3 independent solutions that have the form, this is y2, have the form e to the rt, r equals 1, and then t e to the rt. Again, that's what we're used to from the CC solved case. And then now we just keep going with powers of t, right, until we stop at 1 fewer than the multiplicity, the k value. All right, so these are the 4 solutions that are generated, and then I am going to take them and look at them and maybe do some analysis, see if they're independent solutions. And again, we can check that using the method discussed in a couple of class notes up. And if you do that, they will indeed turn out to be independent solutions. So the answer will be linear combination of these 4 solutions. So I'm going to write that out here, trying very hard to fit it in. Let's see if I will succeed. Perhaps. Sort of. All right, so that would be my general solution with this particular example.